We're talking a little bit about directed graphical models, and then we're going to switch to undirected graphical models. I still owe you a description, maybe some explanation of the computational complexity of different operations on directed graphical models. And I'm going to leave it on the board, and we're going to discuss undirected graphical models and make a comparison between them. So to remind you, they're also called Bayes nets. They have a hard bias. The hard bias is a set of conditional independence assumptions. Every particular Bayes net, or every particular graph, directed graph, corresponds to a particular set of conditional independence assumptions, typically a very large set. If you have 100 nodes, you would have, and they're connected in various ways, typically you have an exponential number of conditional independence assumptions, so you can't even list them all easily. But in principle, we can list them all this way. Every node is independent, conditioned on its parents, is independent of all its non-descendants. Soft bias, we didn't discuss that. When you define a hard bias with a graph, you are defining not a single model, but a family of models. All models that satisfy these conditional independence assumptions. Okay? There are infinitely many of them. To pin down a specific one, you have to specify the probability distributions, the conditional distributions that sit at every node, just like we saw in the example of the forest fire. How do you choose among those given data? Well, the soft bias that is usually used, not that people don't use the term soft bias for it, but effectively they train these models using maximum likelihood. They don't have to. You have a choice. You can use other bias to train it. What do you do with these networks? I mentioned three things: inference, parameter learning, and structure learning. You can think of parameter learning as applying the soft bias or using the data to derive a maximum likelihood estimate within a particular structure, within a particular graph. And you can think of structure learning as trying to choose the right hard bias, using data to choose the right hard bias. Now, that is kind of an oxymoron if you followed what I was teaching earlier this semester. You don't choose a hard bias, it chooses you, right? What I mean is you don't use data to choose bias, otherwise it's not bias. So when we do structure learning and we allow ourselves to consider different biases based on data, we have to start from some other bias. So usually we would have some kind of prior distribution over the structures. Let me go back to the easier problems. Inference. How do you calculate something like this or something like this? This is the same as this, except here we want the full distribution. Here we want the values, specific values of the set that we care about, given some values of the set that we know about. The answer to both of these is by marginalization. Mostly of the third set, the set I called XM. To remind you, for any particular inference problem, we take the whole set of all the X's, and we partition it into three equivalence classes. Those values, those variables whose values we know, that's what I called X sub O here, for observed. I don't remember what I called them the day before yesterday. Those set of X's whose values we care about, we want to know the distribution over these values or the most likely assignment of these values. And the third set, which is the ones we don't know, we don't care about. The third set we have to marginalize over, namely sum over all possible combinations of values. And that's where the problem is actually, because this would be exponential in the size of xm, and in fact also the size of xt. So if you have a graph with 100 nodes, and you know the value of 20 of them, you still need to marginalize over 80 of them. You need to consider all possible combinations of all 80 of them, and that's not feasible. So inference, which until now has been a straightforward computational problem in the other models we discussed, is becoming a difficult problem. What is inference in neural networks? What is another word for inference in neural network, or what is the inference part in neural network? Can you say it louder? Evaluation, which is just forward propagation. You train the network already during learning. Now you're given a set of inputs, and you propagate the signal forward, and you look at what's in the output. Blazingly fast. Okay? What's inference in linear regression? Hello, wake up. What's inference in linear regression? Yeah? You just put the values into the equation. During the training or the learning, you learn the betas, and now you're just putting values of the covariates in and see what comes out. Trivial. What's inference in decision trees? Same thing. You put the test example at the root, and you let it propagate to the right leaf, and you're done. So inference until now has been trivial. But now inference is not trivial. It's computationally challenging, can be challenging. So there are ways around this, but not in a guaranteed way. Namely, there are situations where you can do this efficiently. For example, if the graph is not a graph but a tree, if it has no meeting paths, cycles, not cycles, but meeting paths, if it's not just a DAG but a tree, then you can do inference efficiently using effectively dynamic programming. There are other situations where you can do something that's equivalent to dynamic programming. We call it belief propagation, where you can effectively calculate the sums of exponential number of combinations using polynomial amount of time. So I'll just mention some of them. Sometimes can be done with efficiently with belief propagation. That's one algorithm. Another kind of very general way that often works is called variable elimination. In variable elimination, you take the summation over all possible variables that you're trying to maximize over. So you have a sum over some x7, and then here inside you have another sum over x3, and here inside you have another sum over x8. These are all inside each other. This list is very long, depending on how many variables you have. And the idea is that if you're able to represent your summation this way, then you don't need to repeat this summation many, many times. You do it once, and then you fit it, you eliminate this variable. This is x8. You eliminate this variable, and then you calculate this sum, and then you eliminate this variable, and calculate this sum, and so forth. That's very easy to do if the graph is a tree. It's tricky to do when the graph is not a tree. It can still be done, but the optimal order in which to do the summation is not trivial to find. In fact, it's NP hard. So optimizing this is NP hard. So in a way, it's an open problem that we believe does not have an efficient solution. There are other ways of doing inference efficiently. For example, doing approximate inference. Methods that are not guaranteed to give you the exact correct answer here or here, but are going to give you an answer close to the truth or with high probability correct. So they go by the generic name of approximate inference. For example, sampling. You can use sampling to do your inference. You will not be guaranteed correctness because of the randomness of the sampling process. So this is actually, excuse me, still an open area. How do you do inference inference efficiently in directed graphical networks is an open area, open problem. It was all the rage about 10 years ago or 5 years ago until deep networks took over and people kind of started forgetting about graphical models, although they're still extremely useful. All right, so this is what I want to say about inference. Let's talk about parameter learning. Given a fixed DAG, a fixed base net, fixed structure, and a lot of training data, how would you derive parameters or estimates for the conditional distributions sitting at each node? Bus tour group. And here we have, what did we have? Rain, storm, I forget, storm. And here we had lightning. I forget what the structure is already. And here we had forest fire. And we had a campfire. Let's just take this example. Let's say your structure, I don't know that this is exactly the same as in the Mitchell example, but let's just say that you have a node that has two parents. And for simplicity, let's assume they're all binary. You need to estimate the parameters of campfire conditioned on bus and and storm. If they're all binary, you need to estimate 4 binary distributions, one for each possible values of these. This could be 0, 1, 0, 0, 1, 1, 1, 0. And for each one of these combinations, you need a binomial distribution or a Bernoulli distribution over, which means you have 4 degrees of freedom or 4 free parameters, 8 parameters if you count also those that sum to 1. How would you estimate these from data? Let's say, how would you estimate probability of C equals 1 given that B equals 0 and S equals 1? How would you estimate it from data? Yeah?
Relative frequency.
Relative frequency. You'll just count, right? It's very simple. You'll just count how many times you saw B equals 0, S equals 1, and C equals 1, divided by the number of times you saw just B equals 0 and S equals 1. And if you have very small counts or zeros, then you may want to smooth. But it's very straightforward. The maximum likelihood estimate for a situation where you have the data is very simple to derive. It might require some smoothing. Often, when we have lots of variables, some of their values are missing. I'm not talking about one particular variable that's always missing, that you might as well ignore it. I'm talking about the fact that out of 100 variables, for any record that you have, typically you might be missing 1 or 2 or 5 or 10. Maybe you couldn't collect it that day. Maybe it was lost. Maybe different variables were collected at different periods. You know, they moved the location of the thermometer. It used to measure the temperature in the north part of the park, and now it measures in the south part of the park. It's a different variable. It's available sometimes here and sometimes there. So you have a large number of records, and many of them are missing some elements. What do you do?
Some kind of count like this where you only count it if you have all the data for a record. And like maybe if the values that are missing are independent of the data, then that doesn't introduce any new bias.
So the suggestion is just ignore the records that are not complete. Is that right?
Independently for each distribution that you're estimating.
Independently for each distribution they're estimating. So is the simplest solution. Just discard records that don't have the values that you need for that node. That might work as long as you're not discarding too much data. So let's suppose that the data is missing at a rate of 1%, namely that any variable in any record has an independent random probability of 1% of being missing. Then if you have 3 parents, you have close to 97% probability of them all being there. And you can afford to throw away about 3% of the data. If you have 20 parents, then maybe not so much. Let's suppose you have a 10% missing rate. Now you can't afford to throw away data even with a smaller number of parents. So there are situations where it would be a reasonable thing to do, and yet throwing away data feels wrong in the sense that there is some information in there. So we may want to find a maximum likelihood solution under conditions of some data is missing. Max likelihood in the presence or with the use of, rather than the presence of, using incomplete data. We didn't discuss how to do that. We're going to discuss how to do that in one of the remaining lectures. There is a family of algorithms that are meant especially for this situation. They're called EM algorithms. Sometimes people refer to it loosely as the EM algorithm, but actually it's not a single algorithm. It's a recipe for making algorithms. So in any particular situation, there would be a different EM algorithm. Sometimes you can't derive one. EM algorithms are meant exactly to give you maximum likelihood solutions when your data is not complete. When the data is not complete, solving the equation, the maximum likelihood equations analytically is usually not possible. Instead, you do an iterative procedure. Let me just give you the bottom line here, and then we'll come back to it when we discuss EM. EM is an iterative procedure that is guaranteed to, under some conditions, to converge and will give you a reasonable solution, but not necessarily a good, it's certainly not the best solution. It's guaranteed to give you a local maximum, but not a global maximum. So in that regard, it's similar to gradient descent. It is different than gradient descent in other ways, but it shares the property that it will give you a local maximum, which means that depending on where you start from your iterations, you may end up in different places. So it's not a perfect solution, but it's a solution. And we often don't know of a better solution, so we often use it. It's a very common algorithm. So going back to this question of parameter learning, the summary is, if you have complete data, it's trivial. It's just relative frequency. Otherwise, if you have incomplete data, we would typically use the EM algorithm, which is an incomplete solution. Not only is it incomplete, but it's computationally somewhat demanding because it's an iterative process. It's not terrible, but if you don't want to have to do it a million times. The last question we should discuss is structure learning. And structure learning, let me mention one more thing. When you do EM in this context, one of the steps is inference. Which means there's a link from here to here. So EM is an iterative procedure, but what you do in each step depends on the situation. In the case of directed graphical networks, when you run EM, in every step you need to solve the inference problem. And we already saw that the inference problem in general does not have a known efficient solution. So learning parameters, maximum likelihood from incomplete data, is doubly tricky. First you have to use EM, and within each step of EM you have to solve the inference problem, which may itself be computationally difficult. When you go to structure learning, the problem is triply difficult. Suppose you somehow have a method for searching the space of graphs to decide which one is better. Let's boil it down to the simplest question. You have two graphs, two sets of conditional independence assumptions, two hard biases to choose from. Maybe they're very similar, they differ only by one link, or maybe they're quite different, it doesn't matter. You have a large amount of data. Let's say you have complete data. How do you choose, based on the data, which of these two graphs is a better representation?
Just test separately on these two graphs and compare the results.
Do separately what on the two graphs?
You use the test data separately on these two models and compare the results.
You say use test data separately on these two models, but I didn't actually give you models, I give you just graphs. Remember that every graph stands for a very large family of models, because I didn't give you the parameters. I just said, here's one graph, x1, x2, x3, and this one is x1, x2, x3. Clearly different graphs, 3 variables. I give you a large amount of data, fully specified for all the variables. Which one is a better description of the data?
Okay, so can we first train the graph with some method of parameter?
Okay, so we first need to train the graph, namely to do parameter learning. We need to do parameter learning on one graph, parameter learning on the other graph, right? And then we take some test data and see how well it fits. Or we can do parameter learning and maybe compare the likelihoods of the training data. But certainly comparing the likelihoods of the test data would be safer. So in order to take one step in structure learning, the simple step of comparing 2 structures, I need to do parameter learning. If I have complete data, parameter learning is trivial. But if I have incomplete data, I need to do EM, which means I need to go to inference. So structure learning requires, as a step in the procedure, many calls to parameter learning. And parameter learning requires, in its procedure, if it's incomplete data, many calls to inference. And inference is a hard problem. Okay? So the situation is pretty bad. In general, it's pretty bad. There are certainly specific classes of graphs where you can do it efficiently, and there are a variety of heuristics and techniques. There's whole books written on it. So it's not like the graphical models are not usable. They're very usable. But there is no neat, clean, guaranteed correct solution that works efficiently on all graphs and all data.
When you fix the graph, is inference still hard, or can you perform that optimization problem just once and then use it throughout the experiment?
So talk about this. This is a very interesting question. So I said this optimization is NP hard. Does it depend only on the structure of the graph? And the answer is I'm pretty sure it does. But once you optimize it, that doesn't mean you have an efficient solution. You just have the most efficient solution possible, right? What it does is it minimizes the degree of the polynomial that it will take you to solve. But how low that degree is, I don't know. Good point. Let me add one more thing about directed graphical models that I already showed you, but I want to keep it here as we discuss undirected ones, and that is likelihood factorization. You can, using a particular graphical model, you can represent the joint distribution as a simple product. First, you label the variables in order consistent with the directed graph, so that if I is smaller than j, you cannot get from j to I following arrows. And then this becomes very simple factorization. It was very easy in our example on Monday to just go down the graph and for every node condition it on its immediate parents, and that's it. Now let us move to undirected graphical models. And just like directed graphical models have a name, have a side name, a brand name, undirected graphical models have a name. They're called Markov random fields. I prefer to use the terms directed and undirected graphical models because they're much more descriptive. They tell you exactly what these are. Undirected graphical models, also known as Markov random fields. MRFs. Undirected graphical models are similar to directed graphical models in the sense that they too specify a set of conditional independence assumptions. But the way they specify them is a little bit different, and as a result, the kind of conditional independence assumptions that they specify are, in general, a little different. Undirected graphical models are most useful when you have a large number of variables that are clearly related to each other. They're not independent, but there is no clear direction flowing. For example, there's no clear causality. Example, the classical example is an image. If you have an image with, 1 million pixels, 1,000 by 1,000, say, the pixels are clearly not independent. If they were independent, the image would look like a blur, like a snow. There is very strong correlation between adjacent pixels. Maybe less correlation as the pixels move further away. But there is no clear direction of causality. It's not that the pixel in a particular location was first determined and then that helped determine the pixels around it and so forth. There's no clear who caused whom or who changed whom. In situations like that, undirected graphical models seem most natural, as opposed to directed graphical models, which are very appropriate when you have a clear causality or a clear story of generation, what came first and then what it influenced later. Remember that in directed graphical models, even though they're very suitable for causal stories, they don't insist that what they're describing is causal. Technically speaking, they're describing just correlations, just dependencies. But often that comes from causality. In the case of undirected graphical models, there is no clear relationship to causality. So let's take the case of an image. Here are the pixels. And let's take this pixel and say, what is it influenced by, or what is it mostly correlated with? And draw an edge to it. These are the neighbors of this pixel. And by putting an edge, we're saying there's a direct relationship, not causality necessarily, but there's a direct correlation, association between these values. Now, to fully define the conditional independence assumptions that we make here, I'm going to define something called a Markov blanket. A Markov blanket is a set of variables that together shield one node from the influence of all other nodes. It's like covering it with the blanket. So in this case, let's say these are all connected. These are fully connected. The Markov blanket for this one, for xi here, is this set. And I will write the conditional independence assumptions as xi is conditionally independent, conditioned on the Markov blanket of xi. So when covered by its blanket, it is independent of everybody else. How do I write everybody else? How do I write everybody else? Should I just write everybody else? Else. So of all the others, I'll just write all else, make them look less personal. All others. By others, we mean not xi itself and not its Markov blanket. This captures the full set, when applied to all xi's, it captures the full set of conditional independence assumptions made by undirected graphical models. This is by convention, right? We decide that this is how we interpret undirected graphical models. This property is called the local Markov property. I'd like to give you several alternative definitions of the independent assumptions, and I'm going to tell you in advance that they're all equivalent. This one is called local Markov property. Let me an alternative way of defining it is to say that this node becomes independent of this node if you condition it on a wall that separates them. So if you condition it on a set of nodes, let's say these, such that there is no longer a path from here to here, then these two become independent. You didn't have to use this. You could use this or this. Any path that separates them causes all nodes on one side of the separation to be independent of the nodes on the other side of the separation. So I would write any subset is independent of any other subset conditioned on any separating subset. If my separating subset was, for example, just these two, they're not separating anything, because you could get from here to here. So the simplest way to think about it is that influence travels along these edges. And if it can travel from one node to another, then the two are potentially dependent. But if you block all paths of travel by conditioning on the nodes on the way, they become independent. This is called the global Markov property. And yet there is a third way of specifying these conditional independent assumptions. Every xi is independent of every xj conditioned on everybody else. As long as x and j are not adjacent. Xi, xj, not adjacent. So this property does not apply to two that are connected to one another. But as long as they're not directly connected with a single edge, if you fix the values of everybody else, the two become independent. This is kind of trivial because it's trivially derived from the global property. because if you fix the value of everything else, you're basically creating a separation between the two. So it's very easy. This is called the pairwise Markov property. It's very easy to see that the global property implies the pairwise property. If any separating barrier causes independence, then when these two are not adjacent and you fix everything, you create a separation barrier. It's also easy to see how the pairwise property implies the local property. And what is a little bit harder to see is that the local property implies the global property, but it's also true for continuous distributions. So the bottom line is whichever one of the three is easier for you to remember or understand is fine. They all mean the same thing. Let's proceed in parallel with the directed graphical models. We have the name. The hard bias is the conditional independence assumptions made by the Markov properties. Factorization. Factorization looks quite different here. The joint distribution over all p variables can be factored in an undirected graphical model as a product of components that depend on only subsets of the parameters. In that regard, it's like here. But the subsets are defined differently. Given a undirected graphical model, you first need to identify all the maximal cliques in the graph. A clique is a set of nodes where all nodes are connected to all other nodes, fully connected set of nodes. A maximal clique is a clique that cannot be grown any further in the graph, that any node that you try to add to it will render it a non-clique. So for example, this is a clique, a very simple clique. Every connected edge is a clique because the nodes, there are two nodes, they're connected to each other. It's not a maximal clique because you can grow it. You can add this node. This clique is a 3-node clique. It's also a clique because all nodes are connected to all other nodes. Is it a maximal clique? Is this a maximal clique? Yes, it is. There's only one node we can potentially add, and if we added this node, it stops being a clique because this node is not connected to this node or to this node. So in this graph, this is a maximal clique, but so is this. These two are also a clique, and you cannot grow it. So there are actually two maximal cliques, and they overlap. Maximal cliques can overlap. Now, if this node, let me take a more complicated example. 1, 2, 3, 4. What are the maximal cliques here? This square is a maximum clique. Every node is connected to every other node. And we cannot expand it any further because if we added this to that clique, it's no longer a clique because this one is not connected to these. So this is one clique. Where is there another clique? The triangle. So there are two cliques here as well. In general, you could have a very large number of cliques, but typically much smaller than the number of nodes. Now, the factorization proceeds with a product of functions on each clique. So this is each maximal clique. C is going to be a maximal clique, all maximal cliques. And for each maximal clique, there's going to be a potential function indexed by that maximal clique that depends only on the nodes in that clique and has parameters that are specific to that clique. There's some similarity here to the factorization there, in that the parameters are specific to that. There are going to be parameters here that are specific to that node. Here it's specific to that maximal clique. I left some space here because to be a bona fide probability distributions, it has to sum to 1. And these functions do not naturally ensure that, so I need a normalization constant here. So there will be a normalization constant called 1 over z, and that would depend on all the parameters. So this is the general form of the factorization in undirected graphical models. It's a product of functions that we call potential functions. One for each maximal clique. We factor the graph into its maximal cliques, remembering that some nodes participate in more than one maximal clique. So now when we do inference, these are going to be paramountly important. When we do learning, parameter learning, this is going to be extremely important, because it will allow us to learn these functions, to estimate them from data that depends only on the variables that belong to that clique. Okay, so we talked about likelihood factorization. We talked about the hard bias. The hard bias is a set of conditional independence assumptions. The soft bias we used is similar. We will use maximum likelihood for training the model given a fixed structure. So once we fix the hard bias, we fix the conditional independence assumptions. We will use maximum likelihood to estimate these parameters. And now let's talk about the computational complexity of all these operations. Starting with inference. You have a big graph. You fully specify these potential functions. So you somehow learned or were given the full specification of the model. And now you're asked to do inference, namely you're given some values for some of the variables, and you're asked about the most likely values of some other variables. How hard is that? The answer is it's about as hard as it is in directed graphical models. Maybe slightly harder, but it's still it's an open problem in the sense that depending on the structure of the graph, sometimes you can do that efficiently, but there is no known efficient solution that will work for any structure of any graph. So the sort of take-home message is inference is generally intractable. But there are many heuristics that often work or work for different classes of graphs. Parameter learning. That means solving the ML problem. Theta is all of our parameters. Theta bar is the vector of all the parameters. Het means estimate. ML means the maximum likelihood estimate. Will be defined as the argmax over all possible parameter values of the likelihood of the data, which is this thing. So I'll write this part. 1 over z of theta, product of the maximal cliques are known. You take a product over all of them. Each one of them has a known form function, but now you need to find the parameters here and here. If you remember the situation with directed graphical models, parameter learning from complete data was trivial, was just relative frequency. Parameter learning from complete data in undirected graphs, anybody wants to guess? Is not trivial, but is doable. You can't use relative frequency because these are not simple conditional distributions like you have here. So let me continue here. ML, maximum likelihood estimation from complete data. Not trivial, but doable. By iterations. Iterative procedure. From incomplete data, so in comparison, this is a worse situation than the graphical models, because here in complete data, it was trivial, not just doable. From incomplete data, you again have to rely on EM, and EM has to call, in each iteration, call an inference. So it's every bit as bad as directed graphical models. And structure learning is again very similar. To do structure learning, you need to come up, since the number of structures is exponential, doubly exponential, you need to come up with some heuristic of searching that space. And within that heuristic of trying many different structures, you have an intermediate step of comparing two structures. Maybe you move from one structure to another, you want to see if it's better or worse. That means you need to fully train both models, as in parameter training, and then compare their quality. And to fully train them, you need to do MLE for each one of them, either from complete data or from incomplete data. So structure learning is that much more difficult than parameter learning. Parameter learning is that much more difficult than inference. And inference is sometimes doable and sometimes has to be done inexactly, approximately. Can you represent the set of no conditional independence assumptions in an undirected graph? Suppose I have 5 variables, and I don't want to make any conditional independence assumptions. I believe that they're all dependent on each other in bizarre ways. Can I represent that in an undirected graph? I see a few heads giving me an answer, not too many. How would you represent, I'm giving you a hint, how would you represent 5 variables in an undirected graph such that no conditional independence assumptions can be deduced from that graph? So click, yeah, fully connected. Connect them all to each other, and then, I shouldn't have even tried. Good enough. Can you represent the same null set of conditional independence assumptions in a directed graphical model? Yes? Yes, I showed you how. I showed you how, right? You start with one node. This is x1, and then this is x2, and this is x3. And every new node is connected to all the previous ones. Different graph, but they both mean the same thing. They both capture the fact that there are no conditional independence assumptions made. In other words, no hard bias. So you can represent at least that set in a DGM or in a UGM. What about the opposite? Every node is independent. All nodes are mutually independent in any set, in any group. Can you represent that in a DGM? Can you represent it in a UGM? You guys are asleep big time.
Yes, you can.
I'm sorry?
Yes, you can.
How?
By just not connecting.
Yeah, just don't connect anything. So it's both a DGM and a UGM at the same time. These are the extreme cases. The more interesting question to ask is, can any set of conditional independence assumptions be represented by DGM? I already answered that for you last time. I said no. Can any set of conditional independence assumptions be represented by UGM? And the answer to that is again no. And now the question is one of them a subset of the other? Is the set of all DGMs a subset of all UGMs, or the other way around? Another way of asking this question is saying, is there a set of conditional independence assumptions that is expressible as a DGM but is not expressible as a UGM, or the other way around? And the answer to both questions is yes, meaning that neither one is a subset of the other. So the right view of the world is all DGMs are here. I'll do it like this. This is the set of all possible conditional independence assumptions that can be made. Set of all sets of conditional independence assumptions can be made. These are all the DGMs. These are all the UGMs. They have an overlap, but they also have parts that are separate. In the overlap, we have the two extreme examples that we discussed, where everything is independent of everything else, and also the other one where everything is, no assumptions are made. Anything could be dependent. Let me give you examples from here and from here. I think I already gave you an example from here. There was this example. Oh, no, I didn't. I'm sorry. I gave you an example here. I'll give it to you again. If you have x1, x2, x3, and x4 connected in a ring. Is this in a UGM? Is it expressible as an undirected graphical model? Is the Pope Catholic? Is 1 + 1 2? I just drew a new UGM for you. I'm just trying to keep you awake. Of course, this is an undirected graphical model, because I drew it that way. The conditional independence assumptions here are very easy to write. x1 is independent of x4 and on x2 and x3 together. Right? This is the Markov blanket for x1. And also, x2 is independent of x3 when conditional on x1 and x4. And I believe these are the only two conditional independence assumptions you can draw from this. This cannot be expressed as a directed graphical model. I'm not going to prove it now. I'm just telling you that it cannot. An example, so this is an example from here. An example from here is a simple V structure. Multiple causes. x1, x2, x3. Reading out this DGM, x1 is x1 independent of x2? You guys don't speak DGM fluently? Is it independent?
Yes.
Yes. What about this? No, they're not. Remember, this is the opposite of what we have at the top. If you know the common child, you created a relationship. That's what we call explaining away. There's no way of expressing both of these together in this kind of structure in a UGM. So to express that these are independent, we need to separate them, right? If I turn this into undirected, now when I don't condition, these two are dependent. And when I condition, they become independent. Exactly the opposite. Okay, think about it at home. Now sometimes, since it's easier sometimes to work in UGM, sometimes in DGM, you may want to try to move from one representation to another if you can. I just argued that you won't always be able to do that. If you start with the model here, there's a model that does not have a representation on the other side, you can't do it. But this set is quite large. And if you started with a representation that is a, say, directed graph, you may want to move to a representation that's an undirected graph because it might be easier for you or you prefer it for whatever reason. How would you do that? There are algorithms that try to help you get rid of the arrows, but they're not guaranteed. Obviously, they're not guaranteed to work because you may have started here, in which case nothing will work. But an important consideration is a situation like this, where you want to remember that these two are supposed to be, you want to remember I didn't write, no, I want to write the values for the directed one. So in the directed one, these are independent, right? But these are not independent. Well, you should have corrected me. You want to in this graph, there is let's see, there's influence. Think about it for a moment. If you know X3, they're not independent. Okay, when you try to move from a DGM to a UGM, you have to pay special attention to parents of a single child, of a same child, so multiple causes of the same effect that are not connected. Because of the problem we have here, that once you remove the arrows, the meaning is reversed. So one of the operations you may need to do before you remove the arrows is to connect them. As a way of showing, remember that in the undirected graphical model, the more connections you have, the fewer conditional independence assumptions you're making. So adding edges means relaxing your constraints. By adding an edge here, you're saying that these two may be related. In fact, that they cannot be made independent anymore. I'm telling you the whole story because there's a funny name to it. In some cultures, in some centuries, parents of a child who are not married are considered immoral. So adding a graph here connecting parents of the same child that were not connected before is called moralizing the graph. Okay? I didn't make it up. Moralizing. So just the only take-home message here is, if you want to convert a directed graphical model into an equivalent undirected graphical model, before you start, you should realize that this may not be possible. You may get stuck. There are some DGMs for which there is no equivalent UGM. Second, if you're trying to do it anyway, one of the first operations you have to do is moralize the graph, namely connect all parents of common children that are not connected. Once you do that, you're still not guaranteed that the result would be the same, but it's a necessary step. I want to mention one more concept, and that is conditional random fields. CRF. Conditional random fields are actually not a different kind of model. They are effectively a regular Markov random field. So CRFs are MRFs. The difference is, the reason they have a separate name and they're quite interesting and useful is not because they describe a different set of conditional independence assumptions or a different way of representing it, but because they're trained slightly differently. The soft bias is different, not the hard bias. They are trained discriminatively in the sense that they are trained to maximize probability of correctness of certain variables. So let me first write it down, then explain it. We will talk about discriminative training in a minute. In the general UGM case, we said you have a bunch of variables. You don't make a distinction between inputs and outputs. And you're ready for any kind of inference. Set any subset of them and ask about the value of some other subset. CRMs are particularly suitable for cases where there are distinctions between the variables. Some of them are typically known, observed, and there are some that are the ones you really care about. In that case, you train the model to maximize not the joint likelihood of the entire. See here, we train this to maximize the joint likelihood of the entire data set. But you train them to maximize the conditional likelihood of the variables you care about, which you typically call the labels, the Ys, the labels, the typical output. So they're trained to maximize training maximizes conditional likelihood of the labels conditionally observed. If what you care about, I'll give you an example. Suppose you have a very large number of variables, and they are connected in myriad ways, but there's just two that you care about, that you're trying to read out later to infer what's in them. If you use standard maximum likelihood training, you will be trying to estimate as best as you can the joint distribution of everything. The distribution over these would be just one small part of it. What a CRF does is it focuses on understanding the dependence of these on the others. These would be your labels, the things you care about. So it maximizes the conditional likelihood rather than the joint likelihood. This brings us to the general topic of generative versus discriminative modeling. Modeling, training, methods. We say about a method, it's a generative method. We say about discriminative training or discriminative methods or discriminative classification. You will often hear these terms used around discriminative versus generative. What they mean is generative modeling or generative classification start by trying to understand the process by which the data was generated. In fact, we often use the term data generation process or data generation story. They try to write down a likelihood function that describes, first of all, it gives you the likelihood of any possible data, but usually does that in parts by describing the process of how the data was generated. A directed graphical model is one good example of that. It says first some decision is made about a bus, whether it arrived or not, and about whether it's a cloudy day or not, and then there's a decision made based on that, and so forth. It describes all the data, whether input or output. It describes how the whole thing is generated together. And then, once you have a likelihood function, you combine it with a prior function, and you use Bayes' formula to create a posterior, and then you use that posterior for your decision making, for example, by finding the maximum of the posterior, returning it as the answer. That's the generative way of doing things. So I will summarize it as try to understand how the data was generated. This gives you a likelihood function. Combine it with a prior, with Bayes' formula, get a posterior, and then use your posterior, for example, by maximizing posterior. So these terms of likelihood and posterior and map, these are all come from a generative approach to solving a problem. If your problem is classification, it's kind of a roundabout way. You're asked just to classify every input into, say, one of two classes, but you're not doing that. You're trying to figure out how the input is generated, right? It's kind of a roundabout way. The alternative would be to say, forget about how the data was generated. Let's just try to figure out the most accurate way we can how to classify it. So linear regression doesn't tell you a story of how the covariates were generated. It just gives you a rule, giving a value of the covariates, what the value of the output should be. Right? Neural networks don't tell you how the input was generated. They don't look at which inputs are more likely, which inputs are less likely. They just say, given the inputs, what should the output be? This falls into discriminative methods, where you go straight for the end result. What you want is maximize the classification accuracy. So come up with a family of classifiers and tweak their parameters to maximize your accuracy. Tune parameters directly to, or to directly, will be non-English here. Optimize classification efficacy. By parameters here, I do not imply that there is a likelihood function. These are parameters of something else, knobs in the machine. So linear discrimination is tweaking a surface so that it maximally separates the positive cases from the negative cases. Not paying any attention to how these cases were generated or how likely they are. So this is going directly for what we care about in the end. Which method is better? You have negative 2 minutes to answer that question. I'll give you a hint, it depends. All right, I'll see you on Monday.